Alright, so hello and welcome. Howdy. We are back. The problem we're going to work on today is basic calculator, LeetCode. Let's see, do I have anything incriminating here before I switch screens? I think we can. Oh, 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 oh. Alrighty, so here we are. Basic calculator on LeetCode, given a string S representing of, oh, okay. I know where this is going. It's like part of me was like, I know what this is gonna be, but another part of me was like, well, not fully expecting. Like, no, this is exactly what it's gonna be. Yeah, I've solved this before a few times. This is not a new question to me. Basic calculator, given a string S representing a valid expression, implement a basic calculator to evaluate it and return the result of evaluation. You are not allowed to use any built-in functions which evaluate strings as mathematical expressions, such as eval. Fair enough. Sure. So we have 4 operations: addition, subtraction, and oh, there's no multiplication, just addition and subtraction. Okay, but we do have parentheses. Oh, that's interesting. And what's this one? And the space. Okay. S represents a valid expression, is not used as a unary operation. Okay, that's nice. Although we could support that too if we wanted to. Negative could be used as unary operation. Oh. Okay. Could be unary. Could be as valid. Alright. There'll be no 2 consecutive operators in the input. Oh, okay, fair enough. Every number in running calculation will fit in a 32-bit signed integer. Nice. All right, that's good. That helps. Okay, so we only have 2 operations, but we do also have the parentheses. The parentheses are kind of a pain in the neck, and we do have a sort of a quote-unquote third operation with a unary operator. So, a few things here. I don't know what the unary precedence. I think the unary operator takes the highest precedence, but it only operates on only operates like if there's parentheses and you evaluate the parentheses. One question is, how do we evaluate parentheses? That's probably the trickiest thing. This is very similar to the problem that we were working on earlier, which, by the way, I actually had to fix that. The parsing. There was a parsing operation that I had to do. We had to do, or I did recently, and that was there's parsing. It was tricky because you have nested brackets, right? That's the deal. So this is very similar to that. This has nested parentheses, and there's actually things in between. So we probably want to write a similar kind of routine where we parse between parentheses in our expression. Yeah, we can parse this into. We could break parsing into. We could break this into 2 pieces: parsing and then processing. Although you could parse as you process, like you could do both the same simultaneously. But we definitely want to do the parsing recursively, I think. And what we're going to do is try to find the last. The parsing and processing we'll do recursively. So when you see, if you see a opening parentheses, then you want to recurse on what's inside the parentheses. You have to find the other opening parentheses. So we can use we're going to use a auto recurse function, and we're going to use indices for the strings I, J, or A and B. I like to use A and B. And then inside of S. So it's sort of like a string view type of thing. Yeah. So you would you'd remove the parentheses and recurse. Find the other parentheses, and then recurse on the string in between. And that's if you see parentheses. If you don't see parentheses, then what you're going to do is, and you evaluate that expression, then return the result. So when you see parentheses, you want to call not just recurse, but I'm actually not sure. I guess if you see parentheses, you have to find the second parentheses, I guess, or the completing parentheses, and you can call a recursion on the interior and return that value. I think you want to do it that way. So this is just going to return what the recursion gives us. S, oh no, it's just from 0 to s size minus 1. And you call the recursion, which is going to return a value. So if you see opening and closing parentheses, that's what you're going to do. What's interesting is that'll give you some number, right? And you want to actually continue processing the string though. So once you get the result of that, that gives you some number. You're going to see some operator. So you either see a parentheses or an operator. And depending on the operator, you're going to do different things. So if it's a plus operator, then you're going to process the string to the right, which could be parentheses or what have you, and take that result and add those two together. So recursively resolve that one as well and add these two together. And then part of the deal there is you don't necessarily know how long that string is going to be. And you might just keep going. Like, in other words, I guess what you need to do is parse out that value as well and add it. So I guess you could just increment your like counter past the plus sign and then process the next element as well. And you can kind of just toggle what you're looking for. If you're looking for an operator or or something else. If you're looking for an operator, you're looking for a plus or a minus. And if you're looking for something else, then it could be a parentheses or an integer. If you see, yeah, so you would move past this point and also recursively solve what that is, and then you would say you're looking for. So you see a plus sign, right? Once you have a value, you would see a plus. You're looking for an operator. You see a plus sign. Now you're looking for another value. It could be parentheses or a digit. If you see another parentheses, again, you're going to parse through and recursively find the integer. And then I guess you have op1 and op2. So you already have op1, you're looking for op2. Once you find op2, then you can evaluate the previous operation and get that number. And now you're still looking for another, you get a number, you're looking for another operation. And if you don't see anything when you're looking for an operation, then you're done. You can just return that value. So you do this both iteratively and recursively, I think simultaneously. If you see a number, so let's say, so you're looking for, you have an operator, you're looking for either a number or an opening parentheses. You can actually just evaluate that number. Like, you can just parse that number. And the way you would do that is you can just go digit by digit until you have the number. And we can make that even a subroutine, which would return the number and then also, well, let's not make it a subroutine. It's actually simple enough where we could put the loop right in there, evaluate the number, and then now you have your number, and then you can keep going that way. It's tricky is you do need to figure out if the negative sign is a subtraction or if it's a unary. So when you're looking for a number, you could find opening parentheses, negative value. So we kind of want to put this into like a state machine type of thing. Like we're looking for operator or first number or second number, right? You have 3 different states. And then, or the next number, or a number, rather, next number maybe. When you're looking for an operator, that's when you can finish. If you're looking for another number, I think you just return 0 if you don't find anything. If it's an empty string, for instance. It's never going to be an empty string, but yeah, so they don't really have much for like error checking things. I guess you just always assume it'll work, the expression. And then finally you have, the unary operators are tricky because you could say if you're looking for a number and you see a negative value, then you assume that you're still looking for another number, but now it's going to be a negative. So we could put a sign in front. So we have an enum for the state. We could say, like, really it's just looking for a number or operator, or expecting a number, expecting operator is the state. If we're expecting a number and we see a negative number, then we have a sign. We're still expecting a number, but we update to make sure it'll be a negative number, to update the sign. And then also, once you find a number, multiply it by that sign. Also, that number, once you find a number, make sure you update that sign. Also, that number, update the sign back to positive and make that number, multiply that number by that sign. So it would be, so you have an int for the sign, s. Actually, sign should be inside. So int sign equals 1. Say const bool expecting number is true, expecting operator true. Actually, both of those need to be okay. Expecting operator, expecting number, and what else do we have? There's a sort of a state that we would be in. I think the initial state is always expecting number. I think you're just initially always expecting a number. I'm going to say for int I equals a, I is less than or equal to b, increment I, const char c is going to be s of I, and we say, so I said if, so we have if the state is, this could be an enum, but we're going to actually just make it a Boolean. State is expecting num. Then we have switch on C. And we're going to say case, 3 cases. Three cases are, it could be an opening parentheses. It could be a, I think it's just this. By the way, I don't think you need the parentheses. Opening parentheses could be a unary negation, and it could be a And it could be also like a current val here. Start off at 0. And it could be, so opening parentheses, unary negation, and it could also be a digit. Oh, I didn't think about that. Kind of want if statements then. Yeah, actually, we'll use if statements then. If c equals. Yeah, switch statements don't work quite as nicely for like ranges of numbers, I think. I think that's kind of where we're going to struggle a bit. It could be opening parentheses, it could be another thing, it could be a digit, could be unary, right? That's what the other one is. And finally, a digit. So if c is greater than or equal to 0, or c is less than or equal to 9, the digits. Yeah, it's going to do different things in each situation. So here we process sub-expression recursively. First, use a stack to determine the ending of sub-expression. Process the unary operation by searching for setting the sign bit to a negative and staying in expecting num state and parsing the next value. In this case, it's somewhat iterative, so we'd say sign equals -1, and the state stays the same. Update. Now there is a question of, are we expecting the next number, or like, do we just, I guess there is a question of, you're not just expecting a number, because you need to know once you've processed the number to update the current value based off of what the number is, and what the current operator is. You could say if you're expecting the first number, then you could just say the current op is null. So we could say there's like an enum for the operators. And the way we would do this is we can have an unordered map for the operators, unordered map of characters to lambda expressions. And this is going to say, this is going to be the ops, and it's going to look like the following. We're going to have standard make pair of two things, utility for the pairs. So we have, not parentheses, that's not an operator, we have plus, and we have minus, and I think these operators themselves, they don't necessarily need to use lambda expressions, but we're going to, just because it's simple enough to do that. We just have const int a, const int b, return a plus b, and yeah, lambda expression there, and then the same deal here. And this is a minus b. And we can say current op is going to be I guess you could say auto current op. So my question is, think you would set auto current op. And what's tricky about this is, I want to say this could be like a null pointer initially. We'll come back to that. But if it's not a null pointer, we want to do something like that. Like if it's basically it's a function pointer. I think you can make it a null pointer. I'm not exactly sure what happens here with this, but we want to have a way of knowing like whether or not our operation is set. And we could just have a Boolean value for that too if we wanted. So yeah, so update assign to 1 after evaluating the expression recursively. Similarly, apply the, so actually we could just start the current op to just be addition. So current op can be ops of addition initially. Apply the current operation to the evaluate expression. So basically every string will just have a 0 plus whatever you evaluate. Updates 1 signed to 1. After evaluating the expression, apply the current operation to the evaluated expression. Update the state to the expecting op state. So these are things we can do now. And this is not const anymore. Just reorganizing this a little bit here. Yeah, so current val is going to be, it's going to be op of, I'm going to call the operation on, or current op, current op of val and current val. And val is going to be a, so, and val is going to be updated to the recursive portion where we put that over here. All right, we didn't get back to we didn't get to that yet, but that's what we're just going to go there. So, okay, so we can, how are we doing on time? It's taking a while. Okay, so parse the given integer from the, multiply by the sign. Reset the sign value to 1. So val equals 0, say int val. And we're going to say parse the given integer from the string and update I accordingly. So actually we're going to say D is going to be C minus 0. And actually you're going to set val equal to D. And we're going to say for I is less than or equal to B, increment I here, and say end, I is less than or equal to B, end, it's going to be S of I is not equal to end, and it's greater than or equal to 0, and S of I is less than or equal to 9. So as long as it's a digit, then what we're going to do is say int const int x is going to be S of I minus 0, or D, let's say. We could just say D, it doesn't have to be. And then we're going to say val equals 10 times val plus D. So we do something like this. Yeah, actually, you don't need to put this I here. You can do it this way. You're going to sort of do, sort of perform this check twice. Oh, actually it's and, not or here. So what else do we have? It's between this and this. You're going to double check greater than equal to 0, less than or equal to 9. Set d, and val is 10 times d plus d, and int val is equal to 0. So you're going to kind of repeat this. So you don't have all extra stuff in the front before. And then you're going to say val times equals the sign. Set the sign to 1. And then we do the same thing we do over here. Sign to 1 after by the sign. Parsed integer. Parse the integer from the string, update I accordingly. Okay. So you're going to move past the integer now. I will start at something past the integer. We want to skip white space. That's one more detail. Skip white space. Yeah, you don't do anything on white space. Sign to 1 after evaluating the expression. Okay. State, we're now expecting an operation, and our current value is now going to be the current operation on current value. Yeah, so this part is like going to be the same on both sides here. Here, you set the sign value to negative, staying in the expecting num state and parsing the next value. Right, so we'll do that. What else did you do? Okay, so we still have to process the sub-expression recursively. And we also need to say we're expecting the other side. We're expecting an operator. What do we do there? Else if state is equal to expecting op. Now we need to do different things. So it's very similar to this here. Have different operators. But notice the unary operator will occur when you're expecting a number, right? That's where the unary operator might appear. So the other operators are just add and subtract. So we don't need to process the sub-expression recursively. We can say if we're expecting an operator, just process the negation operator or subtraction operator by updating the current operation, current op. So current op is going to be equal to C of ops, C. And I think that's really it. I think that's all you do. And the other situation is if you're a plus sign, same deal. So I think it's addition operator. I think that's all you need to do is just if it's not white space. So if C is not equal to white space, or better yet, we could just say if C is either the addition operator, process the given operator, and moving to and expecting num state. And the other stuff, we skip white space. That's why we do want to have an else here for white space. So yeah, skip white space. That's the operators that we're expecting. That's it. That's all you have to do, I think. It's quite the for loop we have going on here, though. It's a lot of comments. There are a lot of comments here. I think we also, yeah, so we still need to do the updating the sign is fine. The only thing we need to change is the use a stack, right? Okay, let's get ourselves a stack. How are we doing on time? 30 minutes, 40 minutes, all right. I mean, this takes a while to go through this. So what we can do is basically loop. Now I did this in Python, I used a substring search, but I think it's probably better to, well, we can, I mean, yeah. We can go character by character. I think that's fine. So we say so there's going to be I equals 0 or A, I or not I. We could use J. Actually, you are gonna move I all the way through. So the way it's going to work is we're going to say, and you just need a count. You don't really need a stack. It's not true. So count equals 1 for i's less than or equal to b, and excuse me, I think that's it actually. I is less than b, and count is greater than 0. And what we're going to do is say we do want to start initial. It's going to be I, so I plus 1. That's going to be the initial value. And yeah, I mean, we can do plus plus I. Initial value of I, count is 1. And we're going to say const char x equals s of I. If x is equal to an opening parenthesis, so it could be another parenthesis, then we're going to increment the count. Else if x is equal to closing parentheses, then we're going to decrement the count. Right? So what's going to happen is we're going to move I through this nested parentheses. We're going to process that first nest one nest at a time, and we're going to move past, I is going to move past the nest, right, when we're done. And we're going to stop iterating when so each time you see an opening parentheses, you increment the count, and then when you see a closing parentheses, you decrement the count. So the next character could be closing parentheses, and immediately this closes and ends the loop. And what's interesting is, no, we're actually going to end up on the last character. Sorry, so what's going to happen is, so you decrement the count, and then you increment I to the next character. So first we move past the first opening parentheses. We see, maybe it's a closing parentheses. We decrement the count to 0. We increment I again to move past that, and then we exit the loop, right? We exit after that. Yeah, so we're always going to be past it. We're going to update. So I is in the right spot. I is passed. And we're going to say recurse on initial, and I guess it'd be I minus 1. So what's also interesting is this initial value moves past the opening braces, opening we're going to say int val is going to be recurse on this opening parentheses, and this is actually going to move, it's going to move past the closing parentheses I, but we actually want to go back behind the closing parentheses and 2 characters, so recurse on 1 index past the initial opening parentheses, parenthesis, and on 1 before the closing parenthesis. The value of I will be 1 past parenthesis. Yeah. So that's kind of interesting. So now we recurse, and now we have our val. So now we could update our sign, and we could say current operation to the evaluated expression. So the way this is going to work is so we get this evaluated expression. Current val is now the current operation of the current value and value. And this is sign times that value, by the way. Yeah, which is normally 1, and then update sign to 1 after valuing the expression, update the state to the expecting op state. So now what's going to happen is this will have this recursion. I will end up in the right spot, past that portion. Now, mind you, we could have, like, let's say we have just a whole bunch of nested parentheses. Oh, so there's one more thing here. So once this is all through and done, we return the current value. Yeah. This might be it. We might be done at this point. We could try some test cases. This might be kind of tricky to get the test cases right. Auto not allowed in template argument. Oh yeah, so you can do declare type of, how does that work, declare type? There's a way to get this right. It's tricky, but expression. Can I not do this the way that I'd like to do this? Declare val, that's interesting. I don't think, get reference forward bad, get reference forward good. Yeah, forwarding references. Oh, I think I made a mistake here. Type T to a reference type, make it possible to use member function, declare type expressions without the need to go through constructors. Interesting. Declare values commonly used in templates for acceptable template parameters with no constructor in common, but have the same member function as return type as needed. Declare value can only be used in unevaluated context, not required to be defined. It is an error to evaluate the expression that contains this function. Formally, the program is ill-formed. This function is ODR used. I forgot what ODR means. What does ODR stand for? One definition rule. Oh yeah, gotcha. Okay. Object is ODR used if its value is read unless it is a compile time constant or written. Its address is taken or reference is bound to it. Reference is ODR used if it is used and its referent is not known at compile time and a function is ODR used. If a function call to it is made or its address is taken, if an object, a reference, or a function is ODR used, this definition must exist somewhere in the program. Violation of that is usually a link time error. Gotcha. One definition rule. It's a little confusing. I'd have to kind of go over what that means again. Declare type, standard declare file, non-default foo. Uses it to, it's a class. So involved. It's a class. It's a template with a type name, add R value reference type, declare value, no exception. Okay. So there could be standard declare value non-default function dot foo function, and you get the declared type of that. So you can construct default dot foo and get the declare value, or you can use the declare value of non-default, because it doesn't have a default constructor, and that'll basically, it kind of stands in as a default constructor, more or less. Oh, that's confusing. Sure. Can we declare type of standard declare value of a lambda? I don't know. We can construct a lambda. It's fine. You could try this. Give that a shot. Expected after declare type. Oh, wait, Bruce. Oh, I see. Does that work? Unevaluated operand. Yeah, okay, so you can't use lambdas. That's kind of weird. Huh. I don't like that. That's kind of annoying. Why can't I... That's really interesting. I mean, you can make them these like function pointers if you really wanted to, I think. I've done this before though. Why is this not working now though? You can do a pointer to a function that takes... I always get this wrong, man. It returns an int, and it takes a constant A, constant B. And these are the function parameters. I always get that wrong. Oh. Oh, no kidding. It worked. Huh. Wow. And I forgot. Where's Recurse? I think you only call that once recursively. Oh. Hey! No kidding. Wow. All right, now we want to set up a whole bunch of test cases. Let's use the example cases. See if it works. Almost certainly there's going to be some error here. Okay. All right. So we got 29 instead of 23. And we got 5 instead of 3. Okay, let's try this one. 2 minus 1 plus 2. Okay. So pretty nifty that that this worked, this idea. So I was right about this. Nice. Nice. You program C++. It's only been, 9 years now. No, 8 years. From 2013 would be 8 years. Well, approaching 9 years. Well, I guess it would be like September of 2013. Or maybe early to 2013, I don't know. Approaching 9 years. All right, so somehow we end up with 5. Okay. So what happens? We were expecting num. We should get 2. And then I see the problem. Because you're going to increment I again over here. That's why. That's an issue. Oh, I see. So both of these. Decrement I. I think it's probably the same issue. Probably the same issue in both instances. Yeah. Let's see. Yep, that was what's wrong. Probably a similar issue here. How are we doing? Hey, there we go. Sweet. Now what's weird about this is I don't know how to generate all the test cases that I want to generate. Yeah. How do we do this? The problem is like we need the right context for everything, right? I think we would need we would actually need to do this recursively too, so we can generate expressions and then within those expressions generate sub-expressions. Yeah, actually generating the test cases for this is kind of challenging. Well, you can write a recursive routine to generate an expression, and then what you can do is you can sort of randomly select between creating two expressions with an addition between the two of them, and like a random number of spaces between the two. So you could put some random number of spaces. You could put some random number of, and you could say like get a random number for like the total amount of for that expression, right? So the total number of characters for that expression will be some other random number. So you generate an expression with a random number of characters, a total, and that expression will be recursive, and you'll generate another expression with it could be random number of spaces and an integer and random number of spaces. It could be that could be it, right? And then the random number of spaces, the total sum is going to be less than the total altogether. So you sort of have like two numbers that add up to the total, or add up to the two random amounts. Could be just need to be less than the total, and then or less than or equal to the total. Also with the random digit, the number of digits in the random number that gets generated. So many pieces, and then you have so you can generate random numbers, and you can generate random operations. So it could be a unary if you're expecting a number. You can do a unary operation. Also, I guess when you generate the number, the unary has to be in front, either in front of an expression. Excuse me, or in front of a number, but it's not going to be. Excuse me, it's not going to be sort of like spaces, a negative number, and then more spaces. So expressions themselves. So actually, the expression itself won't have spaces on the left and right side. But you could, when you add operations, you can add spaces between the expressions in the operation. I guess you could also have space before the beginning of the expression and after the end of the expression. Yeah, you could do that, and that would be so you could do that at the top level when you create the expression, add space to the left and the right. Why not recursively? You would be careful not to do that recursively, because if you want to use a unary operator, you would use a unary operator and an expression, which itself wouldn't be. That's another tricky thing too, is could you have a unary operator with another expression where the expression has a unary operator? So you just have a sequence of unary operators. That's also tricky. You have to avoid that, so you don't. What would you do? You would. Excuse me. Well, I guess you just have to have a check when you recurse, just to make sure with the unary operator that you didn't set a unary operator first. So you just have a boolean, checks that there's like a previous unary operator. And if there is, then you don't select that option in the recursion. So you don't have unaries of unaries of unaries. That would get a little messy. Although we can actually handle that with how we've written this. But so yeah, so you could do recursively generate expressions, and then you just have to handle the randomization by reducing the total number of characters depending on how many random characters you selected for each piece. And you could do a random addition operation, negation operation. Addition, you would have expression on the left, expression on the right, addition, and you concatenate the two, and you have random number of spaces between them. Yeah, you have to be a little careful though. Don't put any spaces in the beginning. I think that's just so that way it's simple for the unary operator. And only have spaces towards the end. At the very top level, you could put spaces in the beginning. So yeah, something like that will do the trick. That seems like a lot of extra effort though to test the code. But we can. Excuse me. We can automate. We can automate the create the tests using. We could probably write a Python script to do that, but that's kind of a lot of extra effort. I don't know, it's not that much extra effort, but it's a bit of extra effort. I don't really want to go into all that. Let's just do a few like other 100 plus 5 minus 20 plus 2 plus negative 30 plus 223 plus 4. Another number minus 20 234 plus negative 22 minus 10 plus 34 minus 80 20 plus 2 minus 1 plus 1. We can do minus minus. Yeah, this 2 3 1 2 3 plus 100 minus 20. I don't know, something like this. Just some random sequence of things. Invalid expression. Nice. I think they said they won't have two operators one after another. Is it because of the okay, what if we just take out the unaries? Oh. Okay. Oh yeah, okay. Huh. I want some unaries in here though. Like, what if we negate this whole thing? How about that? I think that's the only time you could use a unary, because can you maybe do something like this, like subtract, like you have 5 plus negative 20, maybe? How about that one? That's a tricky one. Nested parentheses. That works. Okay. I think we go for it. I don't know. There's probably a bunch of test cases I didn't think about or work on, but hey, we got it. Sweet. We're quite slow, but we got there. Did we get under an hour? Yeah, we did. Not bad. I don't know. I mean, okay, we're not super fast. Pretty slow. I think the reason we're really slow though is because we're doing this recursively. So you might be able to speed this up by not doing it recursively somehow, but I don't know, it's kind of awkward to not do it recursively. I think what you'd want to do is I don't know if you really can. I don't know if that's even. I guess what you could do is, like, instead of recursing, you can iterate through this portion, right? When you open your parentheses, and you can push expressions onto a stack. So you could maybe do this portion iteratively, and then your entire routine is not recursive, and then now you have an iterative solution, and that's a lot faster. That might be the way to do it. Yeah, you just push the previous values that you have. Like you would push whatever you had up to that point onto a stack, and whatever operation you had up to that point onto a stack. And then the tricky thing about that though is you have issues with the sign too. You have like, you may have the unary operator handling that could be awkward. So you may have to push a few things onto the stack. And then when you're done evaluating, then when you see a closing parentheses, that's when you can like pop the previous stack, and whatever number you have now, you could apply it to that value in the stack, previous value in the stack, and then continue parsing. So you can do it that way. That's a more efficient way to do this. That's probably why this is on the slower side, because we're using that recursion, but it uses quite a bit less memory. I'm not sure if the stack really would use that much less memory. So yeah, you could do this on a stack too, I think. It's tricky, but I think you can. It's this is I don't want to say it's like an in-order traversal, but it's really like a post-order traversal. Yeah, because you do the left subtree and the right subtree, and then add them together. So it's very much a post-order or a post-order traversal, which it's not too hard to do with the stack post-order. It actually is a binary tree, a binary traversal. So that was another thing I wasn't sure about. I was thinking like, hey, wouldn't it be really hard to do this recursively, because it's a wouldn't it be really hard to do this because it's a what do they call it? The tree is not a binary tree, but actually that's not true. Each operand and the operation creates two operands. That's two operands create actually a binary tree. And your previous value on the left up to that point is actually always the left operand. So it's always the left result of the tree. So it's actually a binary tree and a post-order traversal over that binary tree. So you can make this a sort of a stack-based solution, iterative stack-based solution, relatively easily as a post-order traversal. One tricky thing here though is how this relates to what we were just doing before. We were parsing out so actually that would be more efficient to do the post-order traversal rather than recursing the way that I'm doing it here. This is actually not the most efficient way to do it. It's actually rather inefficient. Another way to do this would be another way to do this, but this is related to the parsing of a arbitrary depth, arbitrarily nested array, and parsing that array into a sort of array of arrays. That was something. So as I mentioned, that was another kind of item I was working on earlier. That's very similar to this. We had a similar kind of routine, which I did it incorrectly over there, I think. Well, I eventually figured it out, the correct way to do it, but the way I'd done it was not really the best. But actually, the way to do that is also you could do the same kind of approach, because what happens is what you're going to do is the left and the right subtrees, you can push them into an array. So your array is going to be processing. The total array is everything that you've processed up to this point. The left subtree is the left item. The right subtree is the right item. And what's interesting is that, yes, once you've processed the right subtree, the left and the right both become the left subtree, because it becomes the same array that you're appending to. So you can use the same stack-based approach. Just treat, you would push, when you see another element, you can push that in the same way we processed here. You see another digit, you can push or evaluate that, sort of use the top of the stack and evaluate that. With the parsing, you can also add that to the array that you're working on, which is at the top of the stack. It should be. It's not actually at the top of the stack. It's actually your current array, which will be eventually pushed onto the top of the stack potentially. And then you're going to add those elements to that array, and then that's processing the left subtree and the right subtree. And when you see a new array, you push the array you're currently working on onto, that's the left subtree pushed onto the stack. And then you start a new array there. And then when you close that array, that's a right subtree that's being processed. Then you take the top of the stack and push that right value into the top of the stack, and then now that's your working array. Yeah, it's tricky. That's a post-order traversal. So that works for both this binary operators on a basic calculator, and it also works on parsing an arbitrarily nested array of, we'll just say, integers, or could really be any elements, right? I think in Python you could have more than just integers, and then finally you also have, I guess it would be strings, and then finally you also have, if you have an array of nested, you have a nested array of values, and you want to flatten that, you can also do a similar thing where you flatten the left subtree, flatten the right subtree, and combine them. So you can kind of parse left to right in a similar way. Excuse me. So you can go element by element. You don't need to do it recursively, but you can go element by element. Excuse me. And the processing would be similar. You have a stack. So the left subtree and the right subtree. The right subtree would be the next element to the right, and the left subtree. So you process one tree at a time. So you process the left subtree. If it's an array that needs to be flattened, then what you do is you take your current array, push that onto the stack, and then take a look at the flattened array, and you start a new array for that. Right, that would be like seeing an opening bracket. Start a new array. And then if the first element's another nested, you start a new array, you keep doing that over and over until you see something that's not a nested value. Then you would see, or it's like a closing bracket. Now, or just an item, you would see an item, you would push it onto your working array. And then when you see a closing bracket, or it's the last item of the position you're currently working on, which is with the nested array that you're currently working on. Yeah, you just need to know where you are in the index, where you are when you were parsing, so you know where to push, or whether or not you're at the end of the array. That's the only way you can know, is to push indices. Whereas similarly here, when you're operating, you kind of always are aware of where you are because you're in a single string, right? So you don't actually, it's a little bit different. So in that situation, you actually need to have an index so you know where you are when you finish. So that is actually very similar to a post-order traversal of a tree with multiple children. Yeah, so that's not a binary tree post-order traversal. That's a post-order traversal of a tree with multiple children, or just a tree. It's just a post-order of a general tree, not just a binary tree. Whereas this is a little more clear that it's a binary tree that you're post-order traversing. Because that tree, it's a little more complicated because, as I said, on the stack you need to actually know basically which child you finished working on in order to know where you should be, like operating next when you sort of jump from one step to the next in the stack. So really interesting, but yeah, it's the problem. The problem is that because you've already parsed the sort of arbitrarily nested array, you won't know how to because you've already parsed that array, you won't know how to you won't know where your position is globally in your iteration. You only know sort of locally. So that's very much like going through a tree. So that's really interesting. I guess I should practice that, or could practice that in the future. But yeah, that was a question that I had for an interview, and I was pretty upset that I got it wrong, because I didn't use the recursive approach. And the recursive approach is super simple. It's like 5 lines of code, but the iterative approach is a lot more complicated, because you're operating through you're walking through it's a post-order traversal of a general tree rather than a binary tree, which makes it a little bit more complicated. Not that much more complicated, ultimately, not that bad. You just basically just need to know what the last child was that you operated on before you jump to the next stack, the next level. So that way when you jump back, you know where to go, right? I guess you could use the index of the child that you just jumped from, so that when you come back, you can just increment that to the next child. That's probably the easiest way to do it, which is just the index in the array that you're currently looking at. But yeah, so that's interesting. Anyway, so yeah, this is fun. There's a few basic calculator questions. I guess you can update this with more operations and things, and that's sort of how they generate some other hard problems for the calculator. Definitely takes like an hour. I think so. If we have an opportunity to look at this again, I think what we'll do is we'll take a look at the stack-based approach. I think that's not a bad call. Yeah, instead of using this approach, same thing. When I parsed my other routine, I used it. This is not the most efficient way to do this. This actually has some overhead, but there is a way to do it that is more efficient. It's sort of linear time rather than quadratic time. But anyway, all right. So thank you again for watching. Talk to you soon. Have a good rest of your day. I'm not sure what I'm doing next. Like maybe I'm going to. I might decide to pick up another problem, or just take a break and hang out for some time. I probably would solve like 1 or 2 more problems before bed, but I definitely want to take a break, get some food, kind of relax for a bit. So yeah, thanks for watching. Talk to you soon.